Development Pharmaceuticals in association with Higher Secondary Principals Forum.
Students, during last academic year, we started with a new branch of mathematics called as calculus. Now, if you recall, you will remember how did we start this branch of mathematics called as calculus. We started with a lesson or the concept called as sets. Now, what is set? Set is defined as a collection of well-defined objects. We define it as a collection of well-defined objects. And after that, if you recall, in the nutshell, we studied these two lessons, two concepts to be precise, relations and functions. We studied this in nutshell, relations and functions. So today, I will stress upon this concept of the first lesson of 12th standard called as relation. Before starting with the concept, let us understand or recall what is Cartesian product or the cross product. Here we have taken set A and set B, set A and set B. Set A have two elements, namely A and B, whereas set B has two elements, 1, 2. And what is cross product? Cross product or the Cartesian product, A cross B is the set of ordered pairs A, 1, A, 2, B, 1 and B, 2. Now, you remember that if set A has two elements, set B has two elements, then A cross B will have 2 into 2, that is 4 elements. There will be 4 ordered pairs in the cross product. In general, if you have set A consisting of m number of elements, set B consisting of n number of elements, then A cross B will have m into n number of ordered pairs. So, this is called Cartesian product or cross product. And Cartesian product or the cross product we take between any two sets or sometimes a set with itself. Now, as I told you, we will start with a concept called as relation. Okay? The first concept of the first lesson of 12th standard, relation. Now, I will define what is relation. Here the definition is there. Relation is any subset of the cross product. I have told you what is a cross product just now. Relation is any subset of cross product. If I go to the previous example which is already there on the slide, relation from set A to set B here will be any subset of the cross product which is already there on the slide here, A cross B, any subset. There are 4 ordered pairs, and if you know, if I ask you how many subsets will be there for the set A cross B, there will be 2 raised to 4 subsets. 2 raised to 4 subsets. And therefore, I can say that there will be 2 raised to 4 relations for this example, which is already there on the screen. 2 raised to 4 subsets of the cross products will be there, and therefore, there will be 2 raised to 4 relation. So, let me come to the definition. Relation is any subset of the cross product. Now, look at this first statement here. X is related to y. X is related to y if x, y belongs to the relation. The ordered pair x comma y should belong to the relation. And other way will be if x comma y belongs to the relation, then x is related to y. And how we write it? We write it x r y, or we can write x comma y belonging to the relation. Here it is clearly mentioned x is related to y if and only if x comma y belongs to the relation. And here it is given relation R, the notation for relation will be capital R, and relation R is any subset of the cross product. And further few definitions which we have already studied in 11th standard, the domain of the relation. What is the domain of the relation? Domain of the relation is nothing but a set of all the first elements of the ordered pairs belonging to the relation. So, domain is nothing but set of all the first elements of the ordered pairs belonging to the relation. And then you have a definition for range. Range. Range of the relation is nothing but the set of all the second elements y element x comma y, when we say all the second elements, set of all the second elements is called as the range of the relation R. I have already told you what is the notation for relation. Relation R will be denoted by capital letter R. The set B is called codomain. Set B, whole set B is called codomain. It is not necessary that the range is equal to the codomain, not necessary. So, range is a subset of the codomain. Range is the subset of the codomain. Okay? So, let us go to the next slide here. There are types of relations. Whatever I have told you just now, we studied last year, I just recall that. Now, let us study something new. Types of relation. A relation R is called an empty relation. Empty, nothing is there. Relation R is called an empty relation if no element of set A is related to any other element of set A. Now, when I say relation in set A, both the sets are A here. So, I am talking about A cross A. So, a relation R in set A is called an empty relation if no element of set A is related to any other element of set A. Because you remember I told you what is the relation. I told you that relation is a subset of the cross product. Subset of the cross product. For this case, it will be A cross A. Relation is a subset of the cross product. For this case, it will be A cross A. And if you recall last year's sets, when you studied subsets, empty set is a subset of any set. Empty set is a subset of any set, and therefore, it is a subset of A cross A. So, empty set is one of the relation. So, we call it as empty relation. We call it as empty relation, and an example is given here. This is A cross A, this is a set A. Parent set A is 1, 2, 3. Here the parent set A is 1, 2, 3, 1, 2, 3, and below that I have written A cross A, all the ordered pairs, there are 9 ordered pairs because there are 3 elements in the set A, and 3 into 3 becomes 9 ordered pairs. And below that, I gave an example of an empty relation. What is an empty relation? I already defined in the first definition here. Okay. So, empty relation should have nothing in the relation. So, it's just empty. So, R1 given here in the slide, okay, second last line there, R1, this one, R1 is set of all ordered pairs A comma B such that A is equal to X. Now, A equal to X, there is no X here in the set. So, I cannot take any ordered pair, because for this relation to have any ordered pair, A must be equal to X. A must be equal to X. There is no X in the set here. There is no X in the set here, 1, 2, 3, which we have taken, and therefore, this is an example of empty relation. So, this is empty relation. Then there is a second definition here in the second line there. A relation is called a universal relation. A relation R is called a universal relation if each element of set A is related to every element of set A. Each element of set A is related to every element of set A. So, this is the other extreme relation. What is the first extreme relation? The first extreme relation is the empty relation. Empty relation, which I already told you what is empty relation. Nothing is there in the relation. What is this other extreme? The other extreme is all the ordered pairs of the cross products are there. All the ordered pairs of the cross product. That means every element of a set is related to any other element of that set, particular set. So, parent set here is 1, 2, 3, A 1, 2, 3, and I have given an example in the last line here, R2, A comma B such that A is less than or equal to 3. Now, this is the relation R2, A comma B belongs to the relation such that A is less than or equal to 3. Now, this R2 will necessarily contain all the elements. Why? Look at the condition which is given here, A less than or equal to 3. The condition is given A less than or equal to 3. Now, if A is less than or equal to 3, that means I have to take 1, I have to A, the first element I have to take 1, I have to take 2, I have to take 3. Yes, so that means I have to take all the ordered pairs which are there in A cross A here, all the ordered pairs in A cross A, okay, and therefore R2 is nothing but an example of universal relation. They are also called as trivial relation, okay, easy relations, okay. Empty relation and universal relations are also called as trivial relations. Now, for universal relation, you can take an example. Supposing you have a class, your class you can consider crossed with your class, students of your class cross your class, okay. Supposing your class has 60 students, then 60 into 60, 3600 ordered pairs will be there in the cross product of your class, say 12 science, cross 12 science. Now, take an example of a relation. A student is related to any other student if the difference of the height is 5 meters. Difference of the height is 5 meters. I don't think there will be any two students whose difference of the height will be 5 meters. Difference. And therefore, there will be no student from your class related to any other student of your class, because there will be no two students whose difference in the height will be 5 meters. And therefore, the relation where the difference in the height is 5 meters will be an empty relation. It will be an empty relation. Now, still continuing with your example of your class, supposing 12 science cross 12 science, and I take an example, say another example, say student from your class is related to any other student if the students are classmates of each other. Students are classmates of each other. Then every student from your class is a classmate of every student from your class. Yes or no? And therefore, this will become a universal relation. All 3600 ordered pairs of your class will be there in the example which I already gave you. So, difference of the height between two students, it will become an empty relation. 5 meters cannot be a difference. I don't think there will be any two students where the difference of the height will be 5 meters. So, it will be an empty relation. And the second example which I gave you, a student is a classmate of other student, then it will be a universal relation. It will be a universal relation. Now, there is something called as reflexive relation. New definition called as reflexive relation. What is reflexive relation? A relation R defined in set A, is called reflexive if x comma x belongs to the relation for all x belonging to A. Now, what is the meaning of this? That is, if every element of set A is related to itself. It's clearly mentioned here, R is said to be reflexive if every element of set A is related to itself. That is, x comma x belongs to a relation, and very important, it shall be for all. It shall be for all x here. It shall be for all x belonging to A. Not even single x shall not be left out. Even single x shall not be left out from the parent set which we are taking. Now, let us consider an example. Let A be equal to 1, 2, 3, 4. Here, this is an example. This is a parent set which we have taken, and here I have taken an example of a relation R. Okay, relation R. We have taken ordered pairs 1, 1, 2, 3, 3, 4, 1, and 4, 4. And if you see, this relation which is given here is not reflexive. Why? Because I give you one counter example here. 2, 2 does not belong to the relation. 2, 2 does not belong to the relation. You will tell me, sir, 1, 1 belongs to the relation. No. The condition says that it should be true for all x. It should be true for all x. So, one example, counter example is given here, 2, 2 does not belong to the relation. You can also give, no, there will be no other example, only 2, 2 does not belong to the relation, 1, 1 belongs to the relation, 3, 3 belongs to the relation, and 4, 4 belongs to the relation. So, x, x, but it does not satisfy this condition. And what is that condition? For all x. For all x, and therefore, one x is missing there, and that is 2. 2, 2 does not belong to the relation. Now, if I take another example, relation on S, and if I take this as an example, the last one, the last line, relation on S, it should be 1, 1, 1, 2, 2, 2, 3, 3, 4, 4, 4, 1, and 4, 4. These are the ordered pairs in this example, and this is clearly reflexive. Why it is reflexive? Because 1, 1 is there, 2 comma 2 is there, 3 comma 3 is there, and 4 comma 4 is there. If all x comma x, now we are not bothered about a 5 comma 5. We don't require 5 comma 5. You know why 5 comma 5 is not required? Because the parent set does not have element 5. We are bothered about only these 4 elements here. So 1 comma 1, 1 is related to itself, 2 is related to itself, 3 is related to itself, and 4 is related to itself. This relation is called as reflexive relation. Reflexive relation. Supposing you take the example which I gave you on your class, 12 signs, okay, cross 12 signs. And if I take example, the second example which I already gave you, classmate of each other, okay, or you can consider heights are equal. Two students are related to itself. If heights are same, heights of the students are same, then supposing I am the student of that class, then my height is equal to my height, and this will be true for all the students. This will be true for all the students, and therefore height of student X will be equal to the height of student X, and therefore the relation on your class such that X is related to Y, if the heights of the two students are equal, automatically becomes a reflexive relation. Let us move to the next definition, the other type of relation, symmetric relation. What is symmetric relation? Okay, we'll discuss this. Now, let R be a relation defined on non-empty set, R as a subset of, let R be a relation defined on non-empty set A. Okay, A is a parent set which we have taken. Then R is said to be symmetric if the first element is related to the second one, and then the second element shall be related to the first. If X is related to Y, if X is related to Y, then Y should be related to X. It's clearly mentioned here, if X comma Y belongs to the relation, if X comma Y belongs to the relation, then Y comma X should belong to the relation. R stands for relation. Whenever this happens, this is conditional. This is if, okay. If 1 comma 2 belongs to the relation, then 2 comma 1 belongs to the relation. If 1 comma 2 doesn't belong to the relation, we are not looking out for 2 comma 1. So that is conditional. Whereas the previous one, reflexive relation, was not conditional. It must be true for all X. It must be true for all X. It's clearly mentioned here, all X. I have already told you this is very important for all X. Whereas symmetric relation is conditional. It is if 1 comma 2 belongs to the relation, then 2 comma 1 belongs to the relation. That is, if height of student X is equal to the height of student Y, then the height of student Y must be equal to height of student X. An example is given here. Again, set A is taken as 1, 2, 3 and 4. Set A is taken as 1, 2, 3, 4, and the relation R is given 1 comma 1, 1 comma 2, 3 comma 1, 4 comma 1 and 4 comma 4. And this relation, if you check properly, is not symmetric. Why? Because 1 comma 2 belongs to this relation. 1 comma 2 belongs to the relation, but the opposite of that 2 comma 1 does not belong to the relation. See, 2 comma 1 does not belong to the relation. You can also give this example. You can say 4 comma 1 belongs to the relation. 4 comma 1 belongs to the relation, but 1 comma 4 does not belong to the relation. Please remember, to disprove something, one example is more than enough. to disprove. When you are saying it is not reflexive, not symmetric, then one example is enough. Okay? You might have many more examples to disprove, but one example is more than enough to write in the solution. But when you are proving something in affirmative, when you are saying yes, it is reflexive, it is symmetric, then it must be true for all the elements. All the elements. So that's why even if 2, 1 was there in the relation as an ordered pair in this relation, supposing 2, 1 is there, but still it doesn't become symmetric. The reason is 4, 1, the opposite of that will be 1, 4 does not belong to the relation. Whereas the last relation which I mentioned here, relation on S, is symmetric, because 1, 1, the opposite is 1, 1. 1, 2, the opposite is 2, 1 present here. 2, 2, the opposite is 2, 2. 3, 3, opposite is 3, 3. 4, 1, opposite is 1, 4. And the last ordered pair, 4, 4, the opposite is 4, 4. So all the ordered pairs which are required to satisfy the definition of symmetric relations are satisfied by this relation, and therefore it is a symmetric relation. Let us go for the third one, transitive relation. Now, what is transitive relation? Again, let R be a relation defined on non-empty set A, that is R as a subset of cross product A cross A. R is said to be transitive if the first element is related to the second and the second element is related to the third, then the first element should be related to the third. See, it's clearly mentioned here. If X is related to Y, Y is related to Z, then that should imply X is related to Z. It is clearly mentioned here, X must be related to Z. See, I'll repeat again. It is X, Y and Y, Z. X, Y and Y, Z should be belonging to the relation. Then X, Z should belong to the relation. If, this is conditional here, this is conditional, if XY and Y, Z, both these ordered pairs shall be belonging to the relation. If X, Y and Y, Z should belong to the relation, and that should give you X, Z belong to the relation. If XY, YZ belongs to the relation, then X, Z should belong to the relation. Whenever, that is a condition put here, if. Like in the symmetric, this is also conditional. So, if X, Y and YZ belongs to the relation, that should imply X, Z should belong to the relation. So, there is an example here given. Consider a set of natural numbers and the relation are to be less than relation A less than B and B less than C. If A is less than B and B is less than C, then A less than C. Yes? Hence, the relation less than is transitive. Supposing I say height of student X, if height of student X is equal to height of student Y and height of student Y is equal to height of student Z, then height of student X is equal to height of student Z. That's a transitive relation. So, a relation, two students related by equal heights automatically will become a transitive relation. Now, the last definition for today's class, equivalence relation. Equivalence relation. What is equivalence relation? If a relation R defined on set A is said to be an equivalence relation if it is reflexive, symmetric and transitive. It must be all three. It must be reflexive, symmetric and transitive. Now, let us solve some exercises on the relation, whatever we have covered so far, that is symmetric part, reflexive part and transitive part. So, let us take the first problem. I will write a problem on the board. Let exercise, okay, let R be a relation defined on set A equal to set A equal to 1, 2, 3 till 14, numbers are till 14, defined by relation R equal to all ordered pairs x comma y such that y minus 3x is equal to 0. X, y belongs to set A. Examine this relation for reflexivity, symmetric and transitive property. So, we are told to examine whether this relation which is given here with respect to the parent set A here is reflexive, symmetric and transitive. Now, let us start with the solution. Now, relation R which is given here is in the set builder form, and our parent set is not a huge set. It has 14 numbers starting with 1, 2 till 14. Parent set has 14 numbers. So, if possible, you can always write the relation in roster form. This is in the set builder form. So, if possible, we can write it in the roster form. So, let us write in the roster form. Relation R in roster form is equal to, supposing I take first element x as 1. Now, which is the second element y? Because it is clearly mentioned here y minus 3x equal to 0. So, y must be equal to 3 times x, because y minus 3x equal to 0 gives you y is equal to 3 times x. So, easily this will become 1 comma 3. First ordered pair which belongs to this relation is 1 comma 3. If I take the second element as 2, because I start with the next element here 2, alright, in the parent set next element is 2. So, if I take second element as 2, then according to this definition y minus 3x equal to 0, because if you see this ordered pair satisfies this condition, because this is in easier terms it will be y equal to 3x. So, 3 times 1 will be 3. Same way 3 times 2 will be 6. So, second order pair which belongs to this relation is 2 comma 6. And similarly, third one would be 3 comma 9 and 4 comma 12, and that is it. Now, why I said that is over? Because if I take the first element as 5, according to this definition, the y will become 15. 5 3s are 15, and 15 does not belong to the parent set, because it is clearly mentioned here x, y belongs to A. So, 15 does not belong to this parent set, and therefore, these are the ordered pairs belonging to this relation. This is a relation, both these relations are same, This is a roster form, this is a set builder form. Okay. Both these relations are same. I have written it in the roster form, easier form. Now, let us check whether this relation which we have written here is symmetric, transitive and reflexive. We will start with reflexivity first. Okay. Now, what is the definition of reflexivity? Reflexivity means x comma x should belong to the relation. X comma x, there were so many x here, 1, 2, 3 till 14. So, 14 x values of x are there. Now, 1 comma 1 is missing, 1 comma 1 is missing, 2 comma 2 is missing, 3 comma 3 is missing, till 14 comma 14 is missing. So, you can, as I told you, you can give any one counter example. So, I will make a statement here, R is not reflexive, R is not reflexive as 1 comma 1 does not belong to relation. The self relation x related to x, that property is not satisfied by this relation, because we have written clearly here in the roster form the ordered pairs which belongs to this relation, which is mentioned here in the set builder form. So, 1 comma 1 does not belong to the relation, it does not belong to the relation. So, one counter example is enough to disprove something. I already told you that. Okay. So, one counter example is given. You can give an example 2 comma 2 does not belong to the relation. You can give, some of you can give relation 3 comma 3 does not belong to the relation. Some can give 14 comma 14 does not belong to the relation. So, any counter example will serve the purpose. Now, let us check the second one, that is symmetric property. If you say 1 comma 3 does belong to the relation, what about 3 comma 1? I clearly gave you a definition, if you remember. If x comma y belongs to the relation, then y comma x should belong to the relations. If, so 1 comma 3 belongs to the relation, but 3 comma 1 does not belongs to the relation, and therefore I will say R is not symmetric, R is not symmetric as 1 comma 3 belongs to the relation, but 3 comma 1 does not belong to relation. So, one counter example, you can also give this example, 2 comma 6 belongs to the relation, but 6 comma 2 does not belong to the relation. Some of you can give this example, 4 comma 12 belongs to the relation, but 12 comma 4 does not belongs to relation. So, R is not symmetric. So, both answers we got in negative, not reflexive, not symmetric. Let us try the third one. The third one is transitive property. Recall the definition. If x is related to y and y is related to z, and if x is related to y and y related to z, then x must relate to z. For the transitive property, to come true, x related to y and y related to z, then x must be related to z. Now, let us check here. 1 related to 3, and then you ask the question, is there any ordered pair which starts with 3? And I notice that there is one more here. So, see, 1 comma 3 and 3 comma 9 belongs to the relation, but 1 comma 9 does not belong to the relation, and therefore, it does not become transitive relation. I will write clearly the answer here. R is not transitive, R is not transitive as 1 comma 3 and 3 comma 9 belongs to the relation, 1 comma 3 and 3 comma 9 belongs to relation, but 1 comma 9 does not belongs to the relation. This does not belong to the relation. 1 comma 3 and 3 comma 9 belongs to the relation. It is there here, 1 comma 3 and 3 comma 9 belongs to the relation, but 1 comma 9 does not belong to the relation, and therefore R is not transitive. So what are the answers we got? It is not reflexive, it is not symmetric, and not transitive. Let us solve one more problem, exercise 2. I will read the problem for you. Let R be a relation defined on Z, set of integers defined by R equal to all the ordered pairs x comma y, such that x minus y is divisible by 3, and x, y belongs to natural numbers. Prove that this R relation which we have defined here is an equivalence relation. So we will solve this problem on the board. Let us try the first property or first definition, that is reflexive property, whether it is reflexive or not reflexive. But here the problem is saying prove that it is equivalence relation. So it must be reflexive. So here we will take x comma x and let us try whether x comma x for any x belongs to the relation or not. And I will tell you it belongs to the relation because the difference of x and x is equal to 0. X minus x is 0. X comma x belongs to the relation because x minus x is equal to 0 and 0 is divisible by 3. I can write it as 3 times 0. 0 is divisible by 3. It is multiple of 3. Divisibility by 3 is nothing but multiple of 3. So 3 into 0. And this is true for any number. Supposing I take 100 comma 100. 100 comma 100. So what is 100 minus 100? 0. Supposing I take 1000 comma 1000. What is 1000 minus 1000? 0. So any numbers you take, same numbers, in fact x comma x, then x minus x will be 0, and which is multiple of 3, and therefore it satisfies the first condition of reflexivity. This is true for all x, and therefore I will write R is reflexive. The first property is true. R is reflexive, the first property. Let us try the second one, the symmetric property. So symmetric starts with the condition if x comma y belongs to the relation. It starts with the condition if x comma y belongs to the relation. And what does this imply? What is the meaning of x comma y belongs to the relation? Now, x comma y belongs to the relation if x minus y is divisible by 3. So x comma y belongs to the relation implies x minus y is 3 times some k. It is multiple of 3. So 3 times from some k integer. Alright. So x minus y is 3k because it is divisible by 3. Because we said x comma y belongs to the relation. Now this will imply y minus x is equal to 3 times minus k. Y minus, if I change the positions of these two, then it will become 3 times minus k, because we have changed the sign throughout. So 3 times minus k is also multiple of 3, and that means y minus x is divisible by 3. We started with x minus y divisible by 3 and we ended with y minus x is divisible by 3. And what is the meaning of this? Y comma x belongs to the relation. The meaning of this is y comma x belongs to relation. And therefore, this is true for any x comma y. Any x comma y such that x minus y is divisible by 3. Supposing I take 10 comma 1. Example. 10 comma 1 means 10 minus 1 is 9 divisible by 3. 10 minus 1 is 9 divisible by 3. And supposing I take 1 comma 10. 1 comma 10 will give you 1 minus 10, which is minus 9. 1 minus 10 will be minus 9. It's like this here. So, divisible by 3, still divisible by 3. And therefore, whenever 10 comma 1 belongs to the relation, 1 comma 10 also belongs to the relation. And I give you one example. This is true for all x comma y such that x minus y is multiple of 3 or divisible by 3. This is true for all. I told you example cannot prove. So, I gave you example to make you understand, but please don't write an example to prove when the answer is affirmative yes, especially for an infinite set like this. Please don't give an example to prove. You can give example to disprove something. If supposing it is not symmetric, you want to prove that it is not symmetric, then you can give a counter example. For proving, necessarily you take general elements x comma y. If you don't like x comma y, you can use any other notation, a comma b, p comma q, any notations can be used, but please don't use an example to prove. And therefore, R is symmetric. Therefore, R is symmetric. Let us try the third one, third property, transitive property. The transitive property. Supposing if, that is also conditional, the third property is also conditional. So, if x comma y and y comma z belongs to the relation, x comma y and y comma z belongs to the relation. What does this imply? If x comma y and y comma z belongs to the relation, this implies x minus y is multiple of 3. I will take it as k1, 3 times k1, because there is another ordered pair. Y minus z will be equal to 3 times some k2, k1 and k2 integers. So, x minus y is 3 times k1, y minus z is 3 times k2. The reason is x comma y and y comma z belongs to the relation. Now, let me try and get the answer x comma z belongs to the relation. So, let us start with x minus z, the difference of x and z, and I have to prove that this difference is multiple of 3. Now, x minus z, what I will do is subtract y, add y and write z. Okay? In this expression, you just subtract y and add y. So, balanced. That means you are adding just 0. It is balanced. The equation is balanced. And x minus y. What is this x minus y? X minus y is multiple of 3. So, 3k1. What is this y minus z? Y minus z is multiple of 3, that is 3k2. We take 3 common and k1 plus k2. Now, what is k1 plus k2? These are k1 and k2 are 2 integers, and if you add 2 integers, it will be integer again. So, this is 3 times k. So, x minus z is multiple of 3, and multiple of 3 is necessarily divisible by 3. Any number which is multiple of 3 is divisible by 3. So, we started with x minus y and y minus z, and we ended with x minus z multiple of 3. So, if x y and y z belongs to the relation, this implies that, this will imply x comma z belongs to the relation, because we have proved that x minus z is divisible by 3, and therefore R is transitive. R is transitive. Now, what is the question here? Prove that R is an equivalence relation. So, we proved that R is reflexive, we proved that R is symmetric, and we have proved that R is transitive here. And by the definition of equivalence relation, because this relation which is defined here, this relation is reflexive, symmetric and transitive, this proves that the relation is an equivalence relation.
Prudent Scholars, powered by Lupin Pharmaceuticals.